The equipotential surface is an imaginary surface. The potential at any point on that surface is equal. Is an imaginary surface. The potential at any point on that surface is equal. Then work done to move a charge from one point to another point on that surface is also equal to 0. Because the work done to move a charge from one point to another point on that equipotential surface that is also equal to 0. The potential difference between the 2 points on that surface, between 2 points on that surface is equal to 0. That surface is known as the equipotential surface. Potential difference between the 2 points on that surface is also equal to 0, because the potential point at any point on that surface is equal to 0, because it is at that surface is at equal distance from, that is the potential at any point on that surface is 0. Then potential at any point on that surface is equal, so that potential difference between the 2 points on that surface is equal to 0, due to which the work done to move one point from one point to another point is equal to 0. These are the equipotential surfaces. Conservative field. The work done to move a point charge in a closed path is equal to 0. The work done to move a point charge in a closed path is equal to 0, because the potential difference between 2 points in a closed path is also equal to 0. The potential difference between the 2 points in a closed path is equal to 0. The field within that closed path is known as the conservative field, because the work done to move a point charge in a closed path is equal to 0. The potential difference between 2 points in a closed path is also equal to 0, because here if a point unit positive charge is moved from one point to the other point, a unit positive charge is moved from one point to the other point in a closed path, then that is equal to 0, so that the field within that closed path is known as the conservative field. So that that field within that closed path is known as the conservative field, so that the potential difference between the 2 points in a closed conservative field is equal to 0, or that is the work done to move a unit positive charge from one point to other point in a conservative field, it is equal to 0. That is known as the conservative field. Here the potential gradient. Know that the potential V is equal to Q upon 4 pi epsilon naught R. That is the equation for the potentials. As the distance from the point charge increases, the potential goes on decreases. Here you know the relationship between the potential and the electric field. Delta V is equal to minus E dot delta L. In terms of the incremental values of the potential and the incremental value of the distance, incremental value of incremental value of the potentials is shall write here in these forms. These two are related through the electric field. From these equations, the dV by dl maximum, it is equal to limit delta V by delta L as delta L tends to 0. That is the maximum value of the rate of change of potential with distance is known as the gradient of potential. Maximum value of rate of change of potential, maximum value of delta V by delta L, limit delta V by delta L as delta L tends to 0 is known as the maximum value of rate of change of potential with distance is known as the gradient of potential, that is dV by dl. So delta V is equal to minus E dot dl. Shall write that equation as according to the dot product property. It can be written as delta V is equal to minus E delta L cos theta. According to the dot product of the two vectors, this delta V is equal to minus E delta L cos theta. So that delta V upon delta L is equal to minus E cos theta. Delta V upon delta L is equal to minus E cos theta. Cos theta is equal to minus 1 and theta is equal to plus 180 degree. And theta is equal to 180 degree, that is pi. Cos theta is equal to minus 1. Delta L is opposite to the direction of electric field. Delta L is opposite to the direction of the electric fields. Delta L is opposite to the direction of the electric field. For that one, delta V by delta L, it is equal to, that is cos theta is equal to minus 1. That is delta V by delta L is positive. Delta V by delta L, it is equal to positive and theta is equal to plus 180 degree. That is both are in the opposite directions. Now limit delta V by delta L as delta L tends to 0 is equal to dV by dl, that is maximum, that is potential gradient. Here it can be written as E is equal to minus gradient of V. E is equal to minus delta V. Delta V by delta L as delta L tends to 0. Because if delta L is opposite to the direction of electric field, and it is equal to positive. But if the distance tends to 0, cos theta is equal to minus 1 and theta is equal to plus 180 degree, that is delta V by delta L is equal to plus E, that is the electric fields. Okay, but and this delta L is opposite to the direction of the electric field. That is delta L is opposite to the direction. Now if this delta L tends to 0, that is equal to potential gradients, and delta L tends to 0 and there will not be any theta, so that the electric field, it is equal to E is equal to minus gradient of V, minus gradient of V, E is equal to minus delta V. That delta is known as the del operators, because del is dou by dou x, x dou by dou y, ay dou by dou z, az. Delta V is equal to dou by dou x, x dou by dou y, ay dou by dou z, az. Because here del, it is known as these terms. Del V in the cylindrical coordinate system is dou v by dou r, 1 by r dou v by dou pi a pi, dou v by dou z, az in cylindrical coordinate systems. This is for the Cartesian coordinates. Here one thing to be noted here is that the gradient of potential E is equal to minus gradient of potential, E is equal to minus del V. Here potential is a scalar quantity. The potential is a scalar quantity, so that the gradient of a potential, the gradient of a potential is a vector quantity, because V is a potential is a scalar quantity, electric field is a vector quantity. So that if we take the gradient of any scalar, it results in a vector quantity. So that here it is the del V, that is the gradient of potential in cylindrical coordinate systems. Gradient of potential in the spherical coordinate systems, dou V by dou r AR 1 by r dou V by dou theta A theta plus 1 by r sin theta dou V by dou pi A pi. So that the gradient of the potential in all the coordinates, whether it may be Cartesian, cylindrical or spherical coordinate systems, can be determined. So that the gradient of a scalar is equal to a vector quantity, is equal to nested. Now the electric field intensity is negative of the scalar potential. The find E at the point 0, 1, 1, that is V is equal to E naught r cos theta in spherical coordinate systems. The negative, find E at these points. If V is equal to E naught r cos theta in spherical, E is equal to minus del V. Potential is given, you have to determine the that is the electric fields. Since the potential, the gradient of potential is dou V by dou r AR plus 1 by r dou V by dou theta A theta plus 1 by r sin theta dou V by dou pi A pi. That is the gradient of potential in the spherical coordinate systems. Now dou V by dou r is dou by dou r E naught r cos theta is equal to E naught cos theta. Now dou V by dou theta is dou by dou theta E naught r cos theta is minus E naught r sin theta. Dou V by dou pi is equal to dou by dou pi E naught r cos theta is equal to 0. Del V is equal to E naught cos theta AR plus 1 by r plus 1 by r dou V by dou theta E naught r sin theta A theta minus E naught r, that is 1 by r dou V by dou theta A theta E naught cos theta plus 1 by r E naught minus E naught r sin theta. Del V is equal to E naught cos theta AR minus E naught sin theta A theta. P of 0, 1, 1. Now at the point 0, 1, 1, r is equal to 0 plus 1 is equal to root is equal to 1.414. Pi is equal to tan inverse of y by x is equal to tan inverse of 1 upon 0 is equal to pi by 2. Theta is equal to cos inverse of z by r, cos inverse in the that given coordinate values. These the coordinate values of point P are in the Cartesian coordinate systems 0, 1, 1. So that first you have to convert these values of this point P into the spherical coordinate values. To convert the Cartesian to the spherical coordinate systems, for that one that radiance of the sphere, that is r is equal to 0 plus 1 is root 2 is equal to 1.414. Pi is equal to tan inverse of y by x, tan inverse of 1 by 0 is equal to pi by 2. Theta is equal to cos inverse of z by r is equal to cos inverse of 1 upon 1.414 is equal to 50 degree. Now del V is equal to E naught cos theta, that is cos 50 degree minus E naught sin theta minus E naught sin theta A theta. E naught cos theta AR minus E naught sin theta A theta, so that the del V is equal to 0.642 E naught AR minus 0.766 E naught A theta. That is the gradient of potential at a gradient of potential for the given potential at the point P. This is the values. Now shall I discuss about the energy density in the electrostatic field. Here, to determine the energy density in the electrostatic field, consider a point charge Q1 is moved from infinity to point P1 in a medium. Before that medium is free of charge. this medium, it is here, it is a medium, this one it is a medium, it is the free of charge. The for that medium is free of charge, then electric field E, electric field E in the medium is 0. Electric field E in this medium, it is equal to 0. That is, before moving this point charge Q1 from infinity to point P1, this medium is free of charge, and the medium is free of charge, then the electric field within the medium is equal to 0. And the electric field in the medium is equal to 0, and then electric field E in the medium is 0 because it is free of charge. Force exerted on charge Q1 is 0. Force exerted on charge Q1 to move from infinity to point P1, it is also equal to 0. Now charge Q1 at a point in the medium, charge Q1 at a point in the medium produces a electric field E. This charge Q1 in that medium, it is produces electric field E. Now charge Q2 is moved from infinity to point P2. Charge Q2 is moved from infinity to point P2, then force exerted on Q2 due to charge Q1 is work done to move charge Q2 against the direction of electric field E produced by the charge Q1 is, because when Q2 is moved from infinity to point P2, the force is exerted on that charge Q2 due to the electric field produced by the charge Q1 at point P1. So that then when the force is exerted, then the work done to move the charge Q2 from the infinity to the point P2 against the direction of the electric field produced by charge Q1 is that work is potential into charge, so that W2 is equal to Q2 into V21. That is the V2, it is the electric field due to the produced by the charge Q1. Similarly, charge Q3 is moved to point P3, Q3 V31, Q3 V32. If n number of charges are moved, Q2 V21, Q3 V31, Q3 V32 plus dash dash, that is the n number of charges. Here charges are moved in the reverse directions, then it is W4 is equal to Q3 V34, that is Q2 V23, Q2 V24. Then the charge Q1, if first charge Q4 is present, then Q3 is moved, then Q3 V34, then charge Q2 is moved in the, that is in reverse directions, so that Q2 V23, Q2 V24. If the charge Q1 is moved, then Q1 is the work done to move the charge Q1 against the direction of the electric field produced by charge 4, charge 3 and charge 2 is V12, Q1 V13, Q1 V14. So that here the charges are moved in the reverse directions. First one, the charges are moved in these directions. First one, the charges are moved in the directions. First the charge 1 is moved, and then charge 2 is moved, charge Q2, and then the charge Q3 is moved from infinity to point P3, so that the electric field produced by charge Q1, the electric field produced by the charge Q2. So that in that way, here if the charges are moved in the reverse directions, we will be getting this is the equations. Now the total work done to W is E is equal to Q1 into V12, V13, V14 plus dash Vn. Q2 is equal to V21, V23, V24, V24. Q3 is V31, V32, V34. Here the total work done, it is the work done due to the individual charges individual charges except for the charge at which it is placed, because there will not be V11, there will not be V22, there will not be any V33. So that here the total work done is equal to the uh, the magnitude of the charge multiplied by the potential due to the individual charges except for the charge at which it is placed. Sum of the uh, sum of the potentials due to the individual charges except for the charge at which it is placed. So that here 2W is equal to Q1 V1 Q2 V2 Q3 V3 plus dashes. W is equal to 1 upon 2 sigma m is equal to 1 to n Qm Vm, because there will not be the total work done is equal to sum of the potentials due to the individual charges except for the charge at which it is placed. That is, there will not be any presence of V11, V22, V33, Vn. So that from that one the work done, that is the work done, or the energy density W is equal to 1 upon 2 sigma m is equal to 1 to n Qm Em. Now energy density due to a point charges in a medium, that is the total work done. So energy density due to a point charge in a medium W is equal to 1 upon 2 due to a line charge rho v dl line charge, due to a volume charge rho v dv volume charge rho s into t. That is for the different charge distributions. Here this is for the n number of charges, sigma m is equal to 1 to n Qm Em. This is for the point charge. Now shall solve the one of the example, that is the energy density in terms of the electric fields. You know that W is equal to 1 upon 2 integral V rho V V dV in terms of the, that is energy density due to the volume charge distributions. According to Gauss law, in the point form, the del dot D is equal to rho del dot D into V dV. Here this equation it can be modified as minus 1 upon 2 D dot del V. But electric field E is equal to the negative gradient of potentials. So the del V is equal to minus E, D is equal to epsilon naught E. From that one, W is equal to 1 upon 2 epsilon naught E square upon 2. W is equal to epsilon naught upon 2 integral V E square dV. This is the energy density due to the electric fields. Okay. Now we shall solve the one of the example that the potential field in a free space is given by V is equal to 50 upon R, A less than or equal to R less than or equal to B, that is in spherical coordinate systems. So that the volume charge density is equal to 0 for A less than R less than B. Find the energy density in the region A less than R less than B. Here volume charge density is equal to 0 in these regions. For that one, here potential is 50 upon R, E is equal to minus del V. That is, it is given that it is spherical coordinate systems. The gradient of potential in spherical coordinate system is dou V by dou R AR plus 1 by R dou V by dou theta A theta plus 1 by R sin theta dou V by dou pi A pi. That is the gradient of potential in the spherical coordinate systems. Gradient of potential in the spherical coordinate systems dou V by dou R AR dou V by dou theta A theta 1 by R dou V by dou theta plus 1 by R sin theta dou V by dou pi A pi. Now dou V by dou R is minus 50 by R square, dou V by dou theta is dou V by dou pi, it is equal to 0, because this equation for the potential does not consist of the theta and pi. From that one, the electric field is equal to minus 50 upon R square AR. D is equal to epsilon naught E is equal to epsilon naught E, it is equal to minus 50 by E is equal to minus 50 minus 50 epsilon naught by R square AR. Here the minus 50 by r square, because why it is the r is to minus to 1, it is equal to minus 50 epsilon naught, because differentiation of this 50 by r, differentiation of 50 by r, it is minus 50 by r square, so that minus 50 epsilon naught by r square. Now the rho v is equal to delta t is equal to 1 upon r square dou by dou r square dr, plus, because there is only variations in the radial directions, 1 by r square dou by dou r square into 50 epsilon naught by r square is 1 upon r square. Here one thing that I have made is that minus 50 by r square, and from that one it will become 50 by r square, so that because here it is minus 50, differentiation of r, it is also minus 50, so that it will become plus. Here it is plus. One by r square dou by dou r 50 epsilon naught, 50 epsilon naught, it is equal to 0, because dou by dou r, it does not consist of any radial components, so that it is independent of radial components. The rho v, that is volume charge density, it is equal to 0, so that rho v is equal to 0 for a less than r less than b. Now energy density, find the energy density stored in the energy stored in the region a less than r less than b. Here w is equal to 1 upon 2 integral v epsilon naught e square dv. dv in spherical coordinate system is r square sin theta dr d theta dp. So that the energy stored is epsilon naught upon 2 integral v 50 upon r square whole square, r square sin theta dr d theta dp. 8.85 epsilon naught is 854 into 10 raised to minus 12 upon 2. R integral r is equal to a to b, theta is equal to 0 to pi, pi is equal to 0 to 2 pi, 500 upon r raised to 4 into r square sin theta d pi dr. 2500 into 8.854 into 10 raised to minus 12 upon 2 integral r is equal to a to b, theta is equal to 0 to pi, pi is equal to 0 to 2 pi, 1 by r square theta dr d theta dp, minus cos theta 0 to pi minus 1 upon r a to b 2 pi 0, minus cos pi plus cos 0 1 by b minus 1 by a 2. The energy stored WE is equal to 0.139 into 10 raised to minus 6 into 1 by b minus 1 upon a joules. That is the energy stored in the in a sphere of the in a sphere with the given conditions a less than r less than b in the regions. Okay.